Numerical methods are systematic procedures for obtaining approximate solutions to mathematical problems. They replace a difficult symbolic problem with a sequence of simpler arithmetic steps. A computer can repeat those steps until the answer is accurate enough. First, many algebraic and transcendental equations have no convenient closed-form solution. Second, realistic engineering models can contain thousands or millions of coupled unknowns. Third, real components have irregular shapes, complicated materials, and complicated boundary conditions. Fourth, measured input data has noise and finite precision, so an exact symbolic result would not be physically exact anyway. Fifth, systems that change with time are simulated one time step at a time. Finally, engineering design and optimization require many candidate solutions to be compared. Numerical methods are shared by every engineering department. Civil engineers analyze structures and water networks. Mechanical engineers simulate heat, fluids, and vibration. Electrical and electronics engineers solve circuit, power, field, signal, and control problems. Chemical engineers model reactors and separation. Computer engineers use numerical optimization, graphics, simulation, and machine learning. Aerospace and biomedical engineers model flight, blood flow, structures, and medical images. Environmental, industrial, petroleum, and mining engineers use the same ideas for pollution, operations, reservoirs, rock mechanics, ventilation, and resource planning. Numerical error is the difference between a true value and an approximate value. For example, 3.14 is a useful approximation to pi, but it is not exact. The true error keeps its sign. The absolute error records only its size. The relative error compares that size with the true value. And percentage error expresses the same ratio as a percent. Input error comes from uncertain measurements. Modeling error comes from assumptions such as neglecting friction, heat loss, or small deformations. Truncation error appears when an infinite process is stopped or a derivative is approximated using finite steps. Round-off error appears because a computer stores only a finite number of binary digits. Let the true value be pi, and let the approximation be 3.14. First subtract the two values and take the absolute value. Next divide the absolute error by the true value. This gives a relative error of approximately 0.000507. Multiplying by 100 gives a percentage error of about 0.05%. This small percentage explains why 3.14 is often useful. Solving an equation numerically means finding a root, a value of x for which f of x equals 0. An algebraic equation is formed from powers of the unknown, as in x cubed minus x minus 2 equals 0. A transcendental equation contains functions such as exponentials, logarithms, sines, or cosines. These equations frequently require numerical solution. A graph helps us locate a root. The curve crosses the x-axis where f of x is 0. At x equals 1, the function is negative. At x equals 2, it is positive, because the function is continuous. This sign change guarantees at least one root between 1 and 2. The bisection method begins with a continuous function and an interval whose endpoints have opposite signs. Calculate the midpoint C by adding a and b and dividing by 2. Evaluate the function at the midpoint. Keep only the half interval that still has opposite signs at its endpoints. Repeat this process. Every iteration cuts the interval width in half, so the root is trapped inside a steadily shrinking bracket. The algorithm first verifies a sign change. It then computes the midpoint and evaluates the function there. If f of r and f of c have opposite signs, replace b by circa. Otherwise replace a by c. Stop when the function value is sufficiently close to 0, or when half the interval width is smaller than the required tolerance. We will solve x cubed minus x minus 2 equals 0. At x equals 1, the function is minus 2. At x equals 2, it is 4. The product is negative, so a root is bracketed. Iteration 1. The midpoint is 1.5. The function is negative, so the new interval is 1.5 to 2. Iteration 2. The midpoint is 1.75. The function is positive, so the root remains between 1.5 and 1.75. Iteration 3 gives 1.625. With a positive function value, the upper endpoint moves to the midpoint. Iteration 4 gives 1.5625. The value is still positive, so we again reduce the upper endpoint. Iteration 5 gives 1.53125, with a small positive value. Iteration 6 gives 1.515625, with a negative value. The root is now trapped in a much smaller interval. This picture shows the guarantee provided by bisection. The root never leaves the colored interval. Each new interval is exactly half as wide as the previous one. Continuing the same steps gives the root approximately equal to 1.52138. Bisection has predictable convergence. After n iterations, the interval width is the original width divided by 2 to the power n. The midpoint error is no larger than half the current interval width. This gives a guaranteed error bound before the exact root is known. The logarithmic formula estimates how many iterations are required to reach a specified interval. Width. Bisection is simple, stable, and guaranteed when its assumptions hold. Its main disadvantage is speed, and it requires a sign-changing bracket. It can also miss an even multiplicity route where the graph touches the axis without crossing it. A common real-life example is turbulent flow through a pipe. The Colebrook equation is used to determine the friction factor. The unknown friction factor appears inside both a square root and a logarithm. Therefore, the equation is transcendental and must usually be solved numerically. Rewrite the equation as capital F of f equals 0. Select a physically meaningful bracket. Apply bisection. And continue until the friction factor reaches the required accuracy. The resulting friction factor is then used to calculate pressure loss, pipe diameter, and pump power. This calculation is important in civil, mechanical, chemical, environmental, petroleum, and mining engineering. Bisection is useful whenever an engineering quantity changes continuously in a safe interval with opposite signs can be found. These examples span structural, thermal, electrical, chemical, computational, aerospace, biomedical, and industrial problems. Numerical methods provide controlled approximations when exact methods are unavailable or impractical. Always identify the sources of error and choose a tolerance that is appropriate for the engineering decision. For bisection, write f of x equals 0. Locate a sign-changing bracket. Calculate the midpoint. Keep the correct half, and repeat until the error is small enough. A good numerical answer should report more than a number. It should state the method, the stopping tolerance, and an estimate or bound for the remaining error.